Unit 11, Probability and Statistics, Booklet 4, Probability. In this video, we'll talk about different rules such as addition rule, multiplication rule, complement rule, binomial, and hypergeometric distributions. Let's look at complements. So the formula for that is the complement of A is equal to 1 minus A. For something to be a complement of something, those parts equal a whole, 100%. Example, if a bag was on sale for 40% off the original price, what is the percent of the original price is the sale price? Well, we have 100% for the original price, and it was 40% off, so we're going to subtract 40%. We get 60%. The percentage of the original price is the sale price would be 60% of that original amount. Let's look at addition rule, not mutually exclusive. They have shared traits. The formula for that would be to add the probability of the first item plus the probability of the second item minus the probability of them sharing both of those items at the same time. Example, a litter of kittens consists of 1 gray female, 3 gray males, 1 black female, and 2 black males. You randomly pick 1 kitten. What is the probability that the kitten is gray or female? So in this case, P of A would be the probability that the kitten is gray. So we have 1 gray, 4 grays. So it's going to be 4 grays altogether. And the probability of B would be how many are female. We have 1 female, 1 female. There's 2 females altogether. And then the probability of having both at the same time, gray and female, would be 1. 1 gray female. And then the total is 7 kittens. So we have 4 gray plus 2 female minus 1 gray female, all over 7 kittens. So your answer is 5 out of 7 chance that the kitten is either gray or female. Let's look at addition rule, mutually exclusive. That means there's no shared traits. The formula for that is just adding the probabilities together. There's nothing that they have together at the same time, so you would just add them together. Example, a box of chocolates contain 3 milk chocolates, 4 dark chocolates, and 5 white chocolates. You randomly select a chocolate. What is the probability that it is a milk chocolate or a dark chocolate? So we will have the total amount of chocolates. 3 plus 4 plus 5. 12 chocolates total. And then the probability A would be milk chocolate. There are 3 out of 12 milk chocolates. And then the probability of B, which is dark chocolate, there are 4 out of 12 dark chocolates. And then the total, you just add them together. 3 twelfths plus 4 twelfths equals 7 twelfths. Reduce the fraction only after you've added them together. These two could reduce, but they would no longer be the same denominator. That's why we would reduce them at the end. In this case, you wouldn't reduce the answer at all. At the bottom of this page, write the answer to this. What are the differences between addition rule mutually exclusive and not mutually exclusive? Basically, compare and contrast these two examples above. Pause the video, write your thoughts about that, and then continue to the next page of the booklet. Alright, let's look at this next page. Multiplication rule dependent. Correct possibilities without replacement. So to get that, we're going to multiply the probability of A times the probability of B given A, or the probability of B times the probability of A given B. And if you have more than just two categories, you repeat that process. Example, a basket contains 5 apples, 4 peaches, and 3 pears. You randomly select and eat 3 pieces of fruit. For this problem, we want to find the total fruit, which is going to be 5 plus 4 plus 3. 12 fruit altogether. The probability that the first fruit is an apple is going to be the total apples, 5, over the total fruits, 12. The next piece is a peach. There's 4 peaches, but they ate the apple already, so there's only 11 fruit left. They've eaten the apple and the peach, so now there's going to be 10 fruits left, and there are 3 pears. You would multiply these 3 numbers together and then simplify them. You can simplify 5 and 10 as 1 over 2. 4 times 3 is 12, so those go away. You're left with 1 over 11 times 2, that's 22. Multiplication rule independent. Correct possibilities with replacement. This way you just find the probability of the first thing times the probability of the next thing, and then just keep multiplying until you get to the end of the probabilities that you need to find. Example, a spinner has equal chance of landing on each of its 4 numbered regions. You spin 5 times. What is the probability that the first spin lands on region 1 and the remaining spins lands on region 3? So draw a spinner. We have 4 equal parts. And what's the probability of it spinning in region 1? The first time, that's going to be 1 out of 4 possible. The rest of them land on region 3. Well, it's still 1 out of 4 for even region 3. And that's going to be 5 times altogether. So we're just going to have 1/4 times 1/4 times 1/4, 5 different times. So that's going to give you 1 over 4 to the 5th power. 1 over 1024. Underneath these 2 examples, write out the differences between the dependent and the independent multiplication rule. Compare and contrast these 2 examples above. Write your thoughts below. Pause the video, write these out. Once you're done, continue with the video. Next, we have the binomial theorem. You have a binomial raised to nth power. Using this formula, you can find any of the terms in the polynomial, or you can expand it out entirely. Let's look at an example. Expand x minus 3 squared. When it's squared, you could just do box or FOIL. But for the purpose of this booklet, let's go ahead and use this formula right here. For the example, we have a is going to be x and b is -3. N is 2, given this example. We'll plug them into the formula. So we have n factorial, so we have 2 factorial over 2 factorial, 0 factorial. X to the second power, -3 to the 0th power. And then we'll add the next term. 2 factorial over 2 minus 1 factorial, 1 factorial. X to the 2 minus 1 and -3 to the first power. And then we'll do the next term. 2 factorial over 2 minus 2 factorial, 2 factorial. X to the 2 minus 2 power times -3 to the second power. It's expanded. We're going to have one more term than there are n's. From here we can simplify this expression right here. 2 factorial over 2 factorial, those cancel. 0 factorial equals 1. -3 to the 0 power is just 1. So we have x squared as our first leading term. Okay, for the next term we have 2 factorial over 2 minus 1 factorial, that's just 1 factorial. 2 over 1, that's just 2. And then we have x, and then times -3. -3 times 2 is -6, -6x. And then the last term, the constant, these 2 factorials cancel out. That's 0 factorial. Again, that's just 1. This is x to the 0 power, that's 1. -3 to the second power, that's equal to 9. So our expanded form is x squared minus 6x plus 9. Let's look at the other example. Find the third term of the expression, 4x minus 7 to the 5th power. We'll identify a, b, n, and k. A is 4x, b is -7, n is 5, and k is going to be 3. From there we plug it into this formula right here. So we have 5 factorial over 5 minus parentheses 3 minus 1 factorial, 3 minus 1 factorial, 4x to the 5 minus 3 minus 1 times -7 to 3 minus 1. And then we'll simplify this. Alright, so 5 factorial is the same thing as 5 times 4 times 3 factorial. We have 64x to the 3rd power, and then times 49. Okay, we could cancel out some stuff. The 3 factorials cancel. The 4 turns into a 2 because 4 divided by 2 is just 2. And then let's multiply those numbers together. 5 times 2 times 64 times 49. So we have 31,360 x cubed. And that is the third term of that expression. Let's look at this page. We have binomial and hypergeometric distributions. Let's look at the first example. It's a binomial of n of a type with replacement. An archer has a 30% chance of hitting the bullseye on a target. What is the probability that the archer will hit the bullseye exactly 3 out of 5 times? For this example, we're going to use the binomial formula. We have n choose x, p to the x power times 1 minus p to the n minus x power. So n choose x is the same thing as NCR of n comma x. This is what you would put into Desmos. And also this is what you would put with factorials. N factorial over x factorial n minus x factorial. If you refer back to the previous booklet, it's combinations without repetition. Now let's define each of our variables. So n is the number of the fixed trials. It's going to be out of 5 times, so n is equal to 5. X is the number of successes. We want exactly 3, so x would be 3. P is the probability of success. That's 30%, or 0.3. From there, you just plug them into the formula, and you can use a calculator for that part. But I do want you to write down, plug it into the formula on your papers whenever you do so. So we're going to have 5 factorial over 3 factorial, 5 minus 3 factorial, times 0.3 to the 3rd power, times 1 minus 0.3 to the 5 minus 3 power. So let's plug those in. So n was 5. Our x was 3, which I just called it r on the calculator. And then p was 0.3. So our probability of exactly 3 out of 5 times would be 0.1323, or about 13%. So we could write it as both a fraction and as a percentage. So that was binomial for exactly. Now let's look at an example where it's at least. Example. A quiz consists of 7 multiple choice questions. Each question has 4 choices. A student who forgot to study guesses randomly on every question. What is the probability that the student answers at least 6 questions correctly? We'll use the same formula as before for binomial distribution. Let's identify our n, x, and p. N is the number of trials here. There are 7 multiple choice questions, so n is 7. X is going to be the number of successes. It says at least 6, so it could be 6 or 7. Correct. So we're going to do the formula twice, one with x being 6 and one with x being 7, and we'll add those 2 results together. P is the probability of getting the answer correct. Each question has 4 choices, so that means there's 25% chance of being correct. So P is 0.25. We'll go ahead and plug it into the formula twice. 7 factorial over 6 factorial, 7 minus 6 factorial, times P, which is 0.25, to the 6th power, times 1 minus 0.25 to the 7 minus 6 power. And then we're going to add that to plugging in x is 7 this time. So 7 factorial over 7 factorial, 7 minus 7 factorial, 0.25 to the 7th power times 1 minus 0.25 to the 7 minus 7 power. So let's plug those in. Let's do it when n is 7, and then we're going to say r is 6. And then p is 0.25. So we'll write our fraction answer. 21 over 16,384. And then add it when our x is 7. 1 over 16,384. They have the same denominator, so we can add those and get 22 over 16,384. And if we change it to a decimal, we have 0.00134 and so on. So we'll say that's approximately 0.0013, and then we'll multiply it by 100 to get the percentage. 0.13% chance. If they ask this kind of question, they could have the answer in fraction form, standard form, or percentage form. Know how to change between those three. Now let's look at the hypergeometric distribution examples. Example: a class has 8 girls and 4 boys. If the teacher randomly picks 6 students, what is the probability that the teacher will pick exactly 2 boys? The formula for this is m choose x times n minus m choose n minus x, all divided by n choose n. What you'll want to write out is the numbers for each of the variables. We have m, x, capital N, lowercase n. And you will rewrite these as NCR of m comma x times NCR of n minus m comma lowercase n comma x divided by NCR of capital N comma lowercase n. This is how the calculator on Desmos will read the formula. Let's identify each of our variables. N is the total population. And so the total population here is the 8 girls and the 4 boys. It's 12 people. Lowercase n is how many are picked in the population. The teacher is randomly picking 6 students. M is the sample size. It's the people that they are wanting to choose, which in this case is boys. So I'll have 4 boys. And then X is going to be the number picked from that sample. It says exactly 2 boys. From there, you just plug them into the formula. We'll have NCR of 4, 2 times NCR of 12 minus 4, 6 minus 2, all over NCR of 12, 6. Then we'll go ahead and put those into the calculator. We have 4 for M, 12 for N, 6 for lowercase n, and then 2 for the x. We have 0.45 repeated, also known as 5 over 11. So that means there's about a 45% chance of picking exactly 2 boys. Let's look at this example. Hypergeometric with at least or at most n of a type without replacement. A gardener has 13 identical looking tulip bulbs, of which 6 will produce yellow tulips and 7 will become pink. She randomly selects and plants 5 of them and gives the rest away. When the flowers start to bloom, what is the probability that at least 2 of them are yellow? So we want to identify our 4 variables. M is the sample size. We're looking at yellow. It says 6 are producing yellow, so M is 6. X says at least 2 are yellow. So that means that they could have 2, 3, 4, or 5. So we could say not 0 or 1. We'll use the complement of this because it's a lot easier to get 0 and 1 because we only plug it in twice as opposed to 2, 3, 4, and 5. That'd be 4 times. And then capital N, we have the total population. There's 13 tulips. And then picked from the population, we have 5. Since it's not 0 or not 1, we're going to have 100% minus the 2 values that we plug into the formula. So if we plug those into the formula, we're going to have 1 minus NCR of M, X, which would be 6, 0 times NCR 13 minus 6, 5 minus 0, all over NCR of 13, 5. And then we're also going to subtract that and replace those zeros with ones. NCR of 6, 1 times NCR of 13 minus 6, 5 minus 1, all over NCR of 13, 5. Let's plug those into the calculator. and then lowercase n is 5, and then the r is going to change from 0 and 1. So we're going to have 1 minus 7 over 429 minus, change that r to a 1, 70 over 429. And then we'll go ahead and type this in. So we have 0.8205. So that's approximately 0.82, 82% chance. All right, go ahead and continue working on your acquisition papers.